Hey everyone, this is Dr. Clyde Letzum, and I'd like to go over resistance. So the way that I like to talk about resistance is I like to start off with an analogy and relate resistance and electricity and the resistance that you get in an electrical circuit to water hose and water. So let's start off with this. Let's say that we have some device here. In this case, we'll just say that it's a water hose. And in this water hose, we have water molecules, of course, okay? And in this case, what happens is we have pressure on both sides. We have pressure P1 and we have pressure P2. Let's say that the pressure P1 happens to be larger than P2. If this is the case, then what we expect is we expect that the water molecule will be flowing from our left to our right. And the reason why we may say this is because that typically if we have some sort of a molecule, let's say let's say you blow up a balloon with air, okay? The air that's inside of the balloon, it's a lot more pressure inside the balloon. If you were to open the mouth of the balloon, what happens is the air would get released from that because the air would be moving from an area of high pressure to lower area of pressure. So that's the same thing that's going to happen in this case. So because P1 happens to have a higher pressure than P2, we expect that the water molecules within the hose will be flowing again from left to right. All right. Given that that's the case, then that the water molecules are flowing from the left to the right. Okay, let's say we wanted to find the rate at which those water molecules are flowing. If we were to look at a specific point here, we can say that the flow rate, and I'm going to use the letter F to represent flow rate. We can say that the flow rate of the water molecules is equal to molecules over seconds. Okay, so one molecule per second we can say is the flow rate in this case. All right, so given that that's the case now, we may find by taking the ratio of the pressure differential and the flow rate of the water, what we may find a resistance that water molecule experiences within the hose. And that ratio tells us that if we take P1 minus P2 from that divided by the flow of the water molecules, that will tell us what our resistance is. So in other words, then, if the flow rate decreases, okay, that means the resistance that the water experiences will actually increase. Okay, so that kind of gives you an idea as to why this is a good equation for the flow rate, or pardon me, for the resistance of that the water molecule will experience within the hose. All right, now let's jump now to our electricity and electrons moving through a piece of wire, or let's say a device in this case. In this case, we know that all devices, all items in nature are made up of atoms, okay? Let's say in this case here, this is some device, and on this end we have some voltage or potential difference, right? Or potential. And on this end we have another voltage or difference, a different voltage on that end, okay? If it happens that the voltage on this end happens to be larger than the voltage on this end, so in other words, V1 is greater than V2, what will happen is we expect electrons then to be flowing through the atom, or pardon me, in this case, we expect the electrons to be flowing through the device going from V2 over to V1. Now, because of some mistake that was done before, we typically say that then the current, okay, that's going to be flowing through this device is actually going to flow through in the opposite direction. And we may say that current, or that flow rate, is equal to, we can say it's equal to, in this case, let's say we can say a certain amount of coulombs per second. And we get coulombs, of course, from the electrons, okay? And so we're just saying that the rate at which we're actually checking here, we can check that to be charge over some period of time, which in this case we can use the units of coulombs per second to represent that in that value. In this case, that rate is going to be our current. Okay, so given that this is the information that we have, if we form a ratio between the voltage differential, okay, and the current within the device, we may find the resistance of that device. Okay, so in other words, then if we take V1 and minus V2 from it and divide it by the I, which is a current, which is the rate of charges over some period of time, okay, we can figure out what the resistance is. So if that rate of charges, if the amount of charges, right, over that period of time actually decreases, that passes that point, decreases, what happens then is we know that the resistance within that device actually went up. Okay, so there's an inverse relationship. All right. So now, given that we understand that, what happens if we were to change the dimensions, the physical dimensions of the actual device? So if we know that the device has a diameter of D and a length of L, we may find a cross-sectional area, that's this area over here, of the device, okay, by taking pi times D over 2, and that D over 2 needs to be squared. That will give us a cross-sectional area of that device. And again, L is equal to the length of that device. Okay? Now, if that cross-sectional area was to be increased, what will happen is we can actually, if we were to check at this point right here, we can see that more atoms or more molecules, pardon me, of water in the case of the hose will actually be able to flow past some given point at any given period of time. So in this case here, we can see that we get 2 water molecules passing through the hose at this point over some period of time. Okay? Or in this case, we can say it's doubled. And so because the rate of molecules passing by some given point increases, what that means then is the resistance of the device decreases. And we can gather that from the equation that we came up with before, which is R is equal to change in P divided by the F, right? Where change in P, remember, is our change in pressure divided by the flow rate. Now, let's consider now if we were to lengthen the device, okay, lengthen that device, what will happen is, because we lengthen the device, the water molecules actually will experience more resistance as it bounces off the edges of the hose. Because it's going to experience more resistance as it bounces off the hose, what we can say then is that the relationship between the resistance and the length is linear. So now, given those two pieces of information from the previous 2 slides, we can find the relationship between the resistance and cross-sectional area to be something like this, where R, which is the resistance, is equal to K, some K, times 1 over A. Okay, where A is a cross-sectional area, and K is some constant. We don't know what it is. And the relationship between the resistance and the length is therefore then equal to K times that length. Okay, now if we combine the 2 of these relationships together, we get that the resistance is equal to some K times L over A. Okay, and the K in this case is what we call resistivity, and we didn't talk about it before, but resistivity is dependent upon the material that the in this case the water molecules or the electron has to pass through. Okay, and so this then gives us an equation in order to find resistance, another equation in order to find resistance. All right. So this again was a discussion on resistance. We will be doing some of this in lab, and we will be looking at resistance and seeing if we can prove or show some of these relationships. Again, my name is Dr. Clyde Letzum. You can find out more about me at my website, www.clydeletzum.com. You can also subscribe to my YouTube channel if you like this video, and if you like some of the others that I've put together, you can go ahead and like my videos. Thanks.